So we're starting today by looking at this chi-square test of homogeneity. I want to introduce the other type of chi-square test. And then we'll do a couple free responses. So starting with this one, our null and alternative here. Remember that with homogeneity, your null and alternative should be about the distributions among the different groups look the same no matter what group we are picking. That's why we're talking about homogeneity, homogeneous groups. So these groups look the same. What are my different groups that I'm comparing? I'm comparing these three different treatments for addiction, and the distribution I'm keeping track of is whether they were effective or not. So the distribution of effectiveness across these three treatments look the same. And then the alternative would be that they don't look the same, or there is a difference between these three treatments in their effectiveness. So that is our hypothesis test here. And I'm going to go pretty quickly through this problem. Chi-square test for homogeneity. That's the name of the test. Conditions. Remember, the conditions are expected counts being at least 5. And then random independent. All expected counts are at least 5. Independent. So there's your 3 conditions. Pause there for about 10 seconds. Free to check. The expected count should be the same. If you put it in a matrix, it should look like one of the columns should all have 16, one of the columns should all have 8. Those are all at least 5. Chi-square test. Again, I would expect you to put the first 2 terms and then put a dot, 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 and then the last term. Degrees of freedom. Number of rows minus 1 times number of columns minus 1. Gives me a p-value of 0.0052, which is less than our alpha level. Rejecting a null hypothesis. Sufficient evidence to conclude that these 3 treatments are not the same. Do not have the same effectiveness. And then we would look at the actual data to see where the difference in effectiveness is. All right, I want to introduce the next type of chi-square test out of these notes, and then we're going to look at some free responses with them. So let's start let's see, wrong slide. No, I don't need these. Here we go. Chi-square test for association and independence is what we are looking at here. The difference between these is going to be your null and alternative, and therefore the conclusion that you make about the alternative in step 4. What we have sufficient or not sufficient evidence for in step 4. Everything else is going to look the same. You're going to put it in the matrix. It's going to be chi-square test on the calculator. All your conditions are going to be the same. The formula is going to be the same. All of that is going to look the same. The thing that it's testing for is going to be slightly different. So the way that you say the null and alternative is going to be the difference maker here. So the chi-square test for association and independence. This is a case where instead of looking at the distribution of two separate groups, we are looking at separate categories within the same group. And we want to know whether those two categories or variables are associated, whether there is any relationship between the two. So our null hypothesis is going to be that there is no association between my variables in the population. And the alternative is going to be that there is an association. The other way you can phrase it, this is also called a test for independence. So you might see it asked, like in the FRQ that we're about to look at, is whether these two things are dependent on each other. So you can say the variables are independent of each other. In other words, they don't depend on each other. And then you can say that they're not independent. In other words, they do depend on each other. That's the same thing as saying no association, there is an association. I'm usually going to state it as no association and there is an association because I think it's more consistent with the null and alternatives that we're used to. Because the null that we're used to is there is no difference or no change. And so I'm going to keep with that. The null is that there's no association between these two variables that I'm measuring. So let me jump down here and point out what the difference between these two tests are. So both the chi-square test for homogeneity and chi-square test of association for independence start with a two-way table and then calculate the test statistic. That is different, by the way, from the other chi-square test we have, which is the goodness of fit. The goodness of fit one is really easy to tell apart. Goodness of fit is when we have one variable that we're measuring. So we just have a plain table with one variable, and we are checking whether the proportions line up the way that they're supposed to. Right, so goodness of fit has one variable. If there are two variables in a table that you're putting in a matrix, then it's one of these two chi-square tests. If, again, let's see, they start with the two-way table, you calculate test statistic, degrees of freedom, and p-value in the same way. All the conditions are the same. The questions that they answer are different. Chi-square test for homogeneity tests whether the distribution is the same for several populations or treatments. So if you have different treatments or separate groups and you're testing whether those groups look the same, that's homogeneity. The chi-square test for association and dependence tests whether two categorical variables are associated in some single population. So the easiest way to tell them apart is by looking at where the data came from. This is near the end of the notes. I think this slide is actually there. It's just later on. If the data come from two or more independent random samples or treatment groups in a randomized experiment, then that's homogeneity. So if we have separate treatments or separate samples that we're comparing, then we're doing a chi-square test for homogeneity. If we are coming from a single random sample, and then we are taking that single random sample and looking at two different categories with them, that's going to be a chi-square test for association or independence. And sometimes the question, like the one we'll look at in just a second, the question is going to literally ask, is there an association? Then you're doing a chi-square test for association. So sometimes the question will make it pretty clear. Sometimes you'll need to look at how the data is getting carried out. So let's actually look at one of these questions so that you can see what I mean. So take a look at these three responses, and we're going to look at number 1. A random sample of 200 students was selected from a large college in the United States. Each selected student was asked to give his or her opinion about the following statement. There's the statement. How important is knowledge of foreign affairs, basically? Each response was recorded in one of 5 categories. The gender of each student was noted. The data are summarized in the table below. Is there sufficient evidence to indicate that the response is dependent on gender? So there's a clue that we're doing a chi-square test of independence, because the question is asking about dependence. The other clue, when we talk about what type of sample do we have, we are not taking our 200 people and splitting them and dividing them up in a random experiment into 2 separate treatments. We are not taking 2 separate samples of 100 and comparing those 2 separate samples. We are taking a single sample and asking them 2 questions, gender and this question about president. And we're looking at within that sample, how does the distribution break down? So the only thing I'm going to write out here is the null and alternative. The null hypothesis. Again, I'm going to phrase it as association, because my null hypothesis is going to be there is no association between response and gender. And then the alternative is that there is an association between response and gender. We're going to use an alpha level 0.05. So the null hypothesis is that there's no association between the 2 variables. The alternative is that there is an association between the 2 variables. Or you could say the null hypothesis is that the response is not dependent on gender, doesn't depend on gender, and the alternative is that the response does depend on gender. So that's your step 1. Now, I'm going to pause here for about 5 minutes or so and let you kind of create, I don't want you to write it all out in detail, but create yourself kind of an outline for how the rest of these steps would go. Because the rest of these steps are going to look the exact same as what we did yesterday. So take about 5 minutes or so to do that. Here's how this looks. We already did our null alternative. Chi-square test for independence or chi-square test for association. That's our formula for the statistic. Again, this formula right here is in your formula sheet. Conditions. The main one they're showing here is here's your expected counts. Here's what they should be. All at least 5. Here's all the individual chi-square values for all the decimal fans out there. And then the chi-square statistic is 8.921. Degrees of freedom is 4. 2 minus 1 times 5 minus 1. which gives me a p-value 0.063. And because that p-value is greater than the alpha level, we're going to fail to reject. Not enough evidence that the response is dependent on gender, or or in our case, not enough evidence that there's an association between the response and the gender. So p-value is greater than our alpha level. We're going to fail to reject. Not enough evidence of an association between the two variables. So that is our process there. All right. Let me move on to the next one. Advertising agency is conducting a survey to determine whether there is an association. There's your type of test, chi-square test for association, because it's asking whether there's an association. You also know that because we are just taking a single sample of 2,500 and asking 2 questions about them. Right? We are not assigning them to any treatments. We are not taking separate samples and comparing them. We're taking a single sample and asking them about 2 different things. So that is, this is going to be a chi-square test of association or independence. So keep that in mind. But let's do the other parts, because there's some probability questions in here. So let's take a look. This will give us a good review. If an adult is selected at random from the sample, that is out of everybody, what is the probability that the selected adult is a college graduate or obtains news primarily from the internet? So, in other words, probability of college or internet. Well, if I want the probability of A or B, then that's going to be the probability of college plus the probability of internet minus the probability of both college and internet. So that equals, I'm moving up here now. That equals, let's see, probability of college is 693 out of 2,500. Plus probability of internet is 687 out of 2,500. And then remember, we subtract the probability of both because we don't want to double count the people who are college graduates and get their news from the internet. So that is minus 245 out of 2,500. Okay, and that equals a number. I don't feel like doing the addition and subtraction right now. Part B. If an adult who's a college graduate is to be selected at random from the sample, what is the probability that the selected adult attains news primarily from the internet? So, if an adult who is a college graduate is selected, what is the probability that they obtain news from the internet? So that is the probability we are selecting from the college graduates. So given college, what is the probability that they get the news from the internet? We're finding the probability of internet given college. So in other words, we are saying out of all of those who are college graduates, so a college graduate is selected at random. So we are going out of all the college graduates, which is 693. What is the probability that they obtain their news from the internet? So out of all the 693 that are college graduates, how many of them obtain their news from the internet? So there's our answer. Part C. Are those two events, college graduate and obtaining news from the internet, independent? Justify your answer. What they are looking for here is a specific property of independence. Independence says that one variable does not affect the other. So we are saying that knowing whether they are a college graduate does not affect where they get their news from. So in other words, this probability that we just found, probability of internet given college versus the probability of internet. They should be the same if the two things are independent. This was actually asked on the practice test you took, and people did not know how to do it. So that's part of why we're doing this part of the question. So probability of internet given college should equal the probability of internet, because what that is saying is that being told that someone is a college graduate does not affect the probability that they get their news from the internet. So we already found this probability up here. This probability is 687 out of 2,500. And these answers need to be exactly the same, are they? No. So that means they are not independent. Because they're not independent, because that means that knowing that they're a college graduate changes my probability that they get their news from the internet. So in other words, those are not independent, because knowing that they're a college graduate changes whether you think they get their news from the internet.
You have to fight for like questions like these work, because I just come up with like what you just said for questions like that. I didn't do any of this work.
It is looking, when it asks if two events are independent like this, it is asking, they're asking for you to compare they're asking for you to know specific properties with probability of independence. Another formula that works for independent, if you can get it, is that the probability for two independent events, probability of A and B equals the probability of A times the probability of B. That's another thing you can check. Is this side of the equation and this side of the equation the same? That's another thing you can check. But the most common one is checking whether these two numbers are the same. They're not looking for like a justification that talks about, the like some type of causing factor between where they get their news and whether they're a graduate or something. They're looking for you to make calculations off of the table and see whether they're the same. Put the fractions. Usually, on a problem like this, the question was about, do we put fractions or going straight to the decimal? Usually, just the fractions will give you the credit. The fractions, convert it to the decimal, will usually give you the credit. The decimal by itself will usually not give you the credit, because the fraction shows me that you know which numbers to put where. The decimal does not tell me that information. So that's why. All right.
That's helpful because I know that all decimals have fractions.
Finally, part D. The company wants to conduct a statistical test to investigate whether there's an association between educational achievement and primary source of news in the city. What is the name of the statistical test that should be used? They're not asking you to do a full 4-step problem here. They're asking you to name the test, which, since we're asking whether there's an association, we're going to put, sorry, that just looks like an X. Let me make it fancier. A chi-square test of association. Chi-square test of association. 30 seconds, get the degrees of freedom. And I would say you should probably show your work for how you're getting degrees of freedom here, since that's all that this problem is asking you to do here. That's time. How many rows? 5. How many columns? 3. Which is 4 times 2 is 8. 8 degrees of freedom.